Greetings, my dear listeners. Today we begin a new journey into the most mysterious and grandiose objects in the universe, the supermassive black holes that hide in the hearts of galaxies. They are often called monsters, devourers, symbols of destruction. But the truth is far more fascinating and profound. These giants, with masses of millions and billions of suns, are not just destroyers, but true architects of the cosmos. Picture a galaxy, our Milky Way, or the neighboring Andromeda. Billions of stars swirl in a slow dance that seems chaotic. But at the very center sits the conductor, a supermassive black hole whose invisible force holds the entire system together. It not only keeps the galaxy bound, but also regulates its development, like a heart pumping blood through a living organism. Once upon a time, astronomers thought such objects were fantasy. The idea of black holes millions of times heavier than the sun seemed impossible. But in the 1960s, strange beacons lit up in the sky. Quasars. They shone brighter than entire galaxies, and no one understood where the energy came from. The mystery proved to be the key. Quasars were fueled by matter falling into supermassive black holes. This discovery changed the picture of the cosmos. We realized that almost every large galaxy hides an invisible titan at its core, and the more massive the black hole, the more closely it is tied to the fate of the galaxy itself. Scientists even discovered a striking correlation. The mass of the black hole is proportional to the mass of the central stellar bulge. This means galaxies and their black holes grow together, like two beings bound by one destiny. Consider how astonishing this is. An object from which not even light can escape becomes the source of brilliance that outshines entire cities of stars. As matter falls into the accretion disk, it heats up and gives birth to light that travels billions of years to reach us. In the death of matter lies hidden beauty and poetry. The stories of the scientists who studied these objects are filled with persistence. For decades they tracked stellar motions, recorded flares, built new telescopes. In 2020, the Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea Ghez for the discovery of the supermassive black hole at the center of our galaxy. They observed stars whipping around an invisible center at incredible speeds and proved there lurks a monster 4 million times the mass of the sun. Philosophically, this discovery reshapes our vision. Supermassive black holes cease to be symbols of an ending. They become symbols of creation, balance, and harmony. They remind us that even in the deepest darkness, there may lie a source of order and beauty. In this first chapter, we are only opening the door. In the chapters ahead, we will speak of how these giants are born, how they govern galaxies, how they create quasars and radio jets, how we study them, and how they influence the fate of the universe. But already we can say, to understand the cosmos, we must understand its architects, the supermassive black holes. In the first chapter, we met the idea that supermassive black holes are not merely destroyers, but architects of the cosmos. Yet an important question arises: how did such giants come into being? Their origin remains one of the most captivating mysteries in modern astrophysics. Picture the early universe. It is only a few 100 million years old. The first stars are igniting, the first galaxies are forming from clouds of gas. And already at this time we observe quasars, beacons whose light has traveled more than 13 billion years to reach us. To shine so brightly, their hearts must have contained supermassive black holes with billions of solar masses. But how could they have grown so huge in such a short span of time? Scientists have proposed several hypotheses. The first is gradual growth. In this scenario, everything began with stellar black holes formed from the collapse of the first massive stars. These black holes slowly grew by consuming gas and colliding with one another. But the problem is that there was too little time. Even if they accreted matter at the maximum possible rate, It would hardly have been enough in just a few 100 million years to reach billions of solar masses. Another hypothesis is direct collapse. Perhaps in the early universe, special conditions existed where massive clouds of hydrogen and helium collapsed directly into black holes with hundreds of thousands or even millions of solar masses. Such heavy seeds would allow them to achieve supermassive scales much more quickly. There is also an even bolder idea. Primordial black holes, formed immediately after the Big Bang from density fluctuations. If they truly existed, they could have served as the seeds for future giants. This hypothesis remains speculative, but the search for such objects continues. Philosophically, the question reminds us that even the mightiest forces in the universe have beginnings. We are accustomed to thinking of black holes as eternal guardians of the cosmos, but they too are born, and the very fact that they appeared so early tells us that nature knows how to act swiftly, almost instantaneously. The history of research into the origins of supermassive black holes reads like a detective story. Some astronomers look for evidence of mergers. Others construct computer models of collapsing gas clouds. Still others hunt for quasars at the highest redshifts. Each new telescope, whether on the ground or in space, brings fresh clues. Yet no final answer has emerged. Perhaps the truth lies in a combination of all three scenarios. Think of it. When we gaze at a distant quasar, we are in fact looking at the infancy of the universe, and within that infancy already lie the giants that will become the architects of the future. In the next chapter, we will explore how supermassive black holes influence their galaxies and why their energy plays a decisive role in the fate of stellar systems. In the previous chapter, we discussed the origins of supermassive black holes. Now it is time to consider how they influence the galaxies they inhabit, and why without them, the universe would look entirely different. Imagine a galaxy as a vast city. It has its neighborhoods, the spiral arms, its squares, the star clusters, and at its very core, the nucleus. And hidden in the very heart of this city lies a supermassive black hole. It is invisible, but its influence extends across hundreds of thousands of light years. When a black hole is active, it ejects powerful jets of plasma into space, streams that pierce through the interstellar medium and reach cosmic scales. These jets can heat gas, blow it out of the galaxy, and thereby regulate the process of star formation. Scientists call this black hole feedback. It is like a thermostat. If stars are forming too quickly, the black hole intervenes to slow the process. If star formation decreases, its activity subsides, and the galaxy is once again free to grow. It is a delicate balance in which destruction becomes creation. Philosophically, this process is striking. It is an example of how a force of destruction becomes a guardian of harmony. The supermassive black hole is not only a symbol of an end, but also a symbol of balance. It recalls ancient deities that embodied both creation and destruction. Observations confirm this. Radio galaxies such as Centaurus A display jets stretching hundreds of thousands of light years. The influence of the central black hole is felt far beyond the galaxy itself. It is as if it signs its name upon the canvas of the cosmos. Without such processes, galaxies would look different. Too rapid a burst of star formation would exhaust the gas and life within them would stall. Modern models show that it is precisely thanks to black hole feedback that galaxies evolve slowly and steadily. This has given the universe the chance to create the diversity of stellar systems and planets, including our Earth. In a sense, we owe our existence to these invisible conductors of the cosmos. Think of it. Every atom in our bodies was once part of a star, and the fate of those stars depended on the balance maintained by the supermassive black hole at the galaxy's core. We are children of stars, but also children of the unseen forces that govern their birth. In the next chapter, we will turn to active galactic nuclei, the brightest and most powerful manifestations of the might of supermassive black holes. We will see how matter, plunging into the abyss, gives birth to light visible across billions of light years. In the previous chapter, we spoke about how supermassive black holes regulate galactic evolution through feedback. Now let us turn to the brightest and most spectacular manifestations of their power: active galactic nuclei. Active galactic nuclei, AGN, are true cosmic beacons. Their light reaches us from billions of light years away. They are so luminous that they can outshine the combined glow of all the stars in their host galaxies. Imagine, from a single point at the galaxy's core comes energy surpassing the radiance of hundreds of billions of suns. Where does this colossal energy come from? The answer lies in the accretion disks of supermassive black holes. Gas and dust falling into their gravitational trap accelerate to unimaginable speeds and heat up to millions of degrees. In this chaos of motion, brilliance is born, the brilliance we call quasars, Seyfert galaxies, or radio galaxies. Different names for different faces of the same phenomenon, the death of matter becoming light. The story of the discovery of quasars deserves a tale of its own. In the early 1960s, radio astronomers detected puzzling sources of intense radio emission. When their optical spectra were obtained, it became clear that they lay at staggering distances. To shine so brightly across such scales, they had to harbor an incredible source of power. Gradually, the realization dawned. This power came from matter falling into supermassive black holes. Philosophically, this discovery is filled with paradox. We see light, but that light is born in death. Matter vanishes in the accretion disk, but its vanishing becomes brilliance that journeys across billions of years. Each quasar tells a story of how an ending becomes a beginning, how death is transmuted into light. Today we know that active nuclei are not just beacons for astronomers. They play a vital role in the evolution of the universe. Their radiation and their immense jets can alter the intergalactic medium, slowing or even stimulating star formation. They act as regulators of cosmic growth, influencing the destiny of entire clusters of galaxies. One of the most striking examples is quasar 3C 273. Its light is visible even in a modest telescope, though it lies 2 billion light-years away. It is like an eye of the universe gazing at us from the deep past. Or consider the radio galaxy Centaurus A, whose jets stretch for hundreds of thousands of light-years, leaving the autograph of its central black hole upon the cosmic canvas. The stories of the scientists who uncovered these objects read like chronicles of perseverance. They faced skepticism, errors, debates, yet step by step they advanced. Today, quasars are not only targets of observation, but keys to understanding the early universe. For in studying them, we peer into a past billions of years distant. Think of it, the light we capture in our telescopes today was emitted when Earth had neither humans nor even complex life. In that sense, quasars are letters from the past, messages from the cosmos to future civilizations. In the next chapter, we will discuss the methods scientists use to study supermassive black holes, for despite their invisibility, we have learned to measure their masses, their motions, and even to take the first photographs of their event horizons. In the previous chapter, we spoke of active galactic nuclei and how they serve as beacons of the universe, but a question remains. How did scientists discover the existence of supermassive black holes at all? For the holes themselves are invisible, no light escapes them. To study such objects requires special methods, and it is these we will explore today. The first and most reliable method is observing the motion of stars. If a galaxy's center contains an unseen object of enormous mass, it will shape the orbits of nearby stars. This is how the supermassive black hole at the core of our own galaxy was proven. For decades, astronomers tracked the star S2, which completes its orbit in just 16 years. Its velocity at closest approach exceeds 5,000 kilometers per second. The only possible explanation is an object 4 million times the mass of the Sun, the invisible giant known as Sagittarius A*. The second method is analyzing the spectra of gas. Gas orbiting a black hole emits light marked by characteristic lines. The shifts and broadenings of these lines reveal the velocity of the material and allow astronomers to estimate the mass of the central object. This approach is especially useful for active galaxies, where bright accretion disks provide ample illumination. A third method involves X-ray and gamma-ray observations. Matter plunging into a black hole heats to millions of degrees and emits high-energy radiation. Modern space observatories such as Chandra and XMM Newton record these bursts, giving scientists the ability to witness accretion almost in real time. But perhaps the most striking achievement of recent years is the direct imaging of the event horizon. In 2019, the Event Horizon Telescope collaboration unveiled the first picture of the shadow of a black hole in Galaxy M87. In 2022 came the release of the image of our own central black hole, Sagittarius A*. These photographs astonished the world. Humanity had glimpsed what was once deemed impossible, the unseen made visible through the collective power of science. Philosophically, this progress is profound. We deal with objects that by definition cannot be seen directly, and yet we have found ways to see them through stellar motions, the glow of gas, and even their shadows. It recalls Plato's allegory of the cave. We do not see the objects themselves, but their reflections and imprints. Yet by studying these shadows we approach truth. The stories of the scientists behind these breakthroughs are filled with persistence. To capture the image of M87*, 8 radio telescopes across the globe had to be linked into one Earth-sized instrument. It was a triumph of cooperation, an example of humanity's ability to unite for knowledge. And the result became not only a scientific milestone, but a cultural symbol, proof that the impossible can be achieved. Think of it. We live in an era when the invisible becomes visible, when the boundaries of human knowledge extend to the event horizon itself, and this is only the beginning. The future may bring sharper images, even movies of accretion in real time. In the next chapter, we will consider how supermassive black holes grow and what they feed upon. For to become architects of galaxies, they had to consume staggering amounts of matter and energy. In the previous chapter, we spoke about the methods scientists use to study supermassive black holes. Now it is time to ask a question that fascinates many. How do these giants grow, and what do they feed upon? For to become architects of galaxies, they had to accumulate masses of millions and billions of suns. Picture a black hole as an insatiable giant. It cannot exist in isolation. To grow, it needs fuel. That fuel comes in the form of gas, dust, stars, and even whole clouds of interstellar matter. Once these fall under its gravitational sway, they plunge inward, forming an accretion disk. Their matter accelerates, heats up, and eventually disappears beyond the event horizon. One of the primary mechanisms of growth is gas accretion. In the early universe, cold hydrogen abounded, gathering into clouds that settled into galactic centers. Black holes drank deeply from this ocean, devouring matter and swelling to monstrous sizes. This, scientists believe, is how the first supermassive black holes grew into the quasars we observe today. Another path is mergers. When galaxies collide, their central black holes drift toward one another until at last they merge into a single entity. Such collisions unleash torrents of gravitational waves, which we can now detect with instruments like LIGO and Virgo. It marks a new era of observation. We not only see light, we also hear the music of colliding black holes. Philosophically, there is a profound lesson here. Even destructive acts, galactic collisions, stellar deaths, become sources of growth. The demise of some objects nourishes the life of others. In the cosmos, there is no final emptiness. Everything is recycled, everything folded into the endless cycle of birth and disappearance. At times, black holes may feed directly on stars. When a star strays too close, tidal forces tear it apart, and its substance streams into the accretion disk. These events, called tidal disruptions, are rare but spectacular, offering scientists the chance to study accretion almost in real time. The history of studying black hole growth is intertwined with advances in computer modeling. Modern simulations show gas clouds falling inward, accretion disks forming, jets hurling energy outward. These models help us understand why some black holes blaze with activity, while others remain quiet and hidden. Think of this, our own Sagittarius. A asterisk is calm today. It feeds little and shines faintly, but millions of years ago it may have been active, casting powerful jets and shaping the destiny of our galaxy. Perhaps these cycles of activity and quiescence, like breathing, define the rhythm of the cosmos. In the next chapter, we will explore how supermassive black holes communicate with their surroundings and how their energy spreads throughout the galaxy and beyond. In the previous chapter, we explored how supermassive black holes grow by feeding on gas, stars, and even whole galaxies. Now let us consider how they interact with their surroundings and how their energy spreads throughout the galaxy and beyond. Supermassive black holes cannot be regarded as isolated objects. They are tied to the cosmos through a complex web of interactions. Their gravity shapes the motion of stars, their accretion disks radiate light, and their jets pierce the intergalactic medium. These processes are known as black hole feedback. They can stimulate or suppress star formation, alter the distribution of gas, and influence the future of entire galaxy clusters. Take, for instance, the phenomenon of jets. These streams of plasma erupting from the vicinity of a black hole can extend hundreds of thousands, even millions of light years. They carry colossal amounts of energy, heating intergalactic gas and preventing it from cooling. Without this process, gas would quickly condense, forming stars in uncontrolled abundance. Jets act as regulators. They prevent the galaxy from squandering its resources too swiftly. Philosophically, it is akin to a stern teacher. The black hole does not allow the galaxy to grow too wildly, holding it in balance. Once again, in destruction we find creation. Energy that might seem chaotic proves to be a mechanism of harmony. Beyond jets, there is another form of feedback: radiation. Active nuclei emit light so powerful that it literally blows gas out of galaxies. Such processes are observed in quasars. The light born from the death of matter becomes an instrument reshaping the destinies of stellar systems. The stories of observation are breathtaking in their scale. In some galaxy clusters, astronomers see enormous cavities in the hot gas, like bubbles blown by the jets of central black holes. These bubbles can exceed the size of our entire galaxy. Their existence is direct evidence that black holes govern their cosmic surroundings on immense scales. Think of this. Energy born within a few light hours of the event horizon spreads across millions of light years. It is as though the breath of a single being could alter the climate of an entire continent. Here lies the marvel of supermassive black holes. They connect the micro and the macro, the small and the vast, the local and the cosmic. Modern models confirm that without black hole feedback, galaxies would look utterly different. They would quickly exhaust their gas supplies, and life within them would stall. But thanks to black holes, the universe evolved gradually, giving rise to complexity and diversity. In the next chapter, we will discuss yet another dimension of this story: how supermassive black holes influence the formation of structures in the universe as a whole, and why they may be called architects not only of galaxies but of the cosmic landscape itself. In the previous chapter, we discussed how supermassive black holes interact with their surroundings and regulate the life of galaxies. But when we take a broader view, we see that their influence extends far beyond individual stellar systems. Today we will explore how these objects shape the very cosmic landscape, becoming architects of the universe's structure. When we look at the map of galaxy distribution, we do not see chaos but a vast network, the cosmic web. Galaxies and their clusters form the nodes of this web, while voids stretch between them. At the centers of many of these nodes lie supermassive black holes. Their energy literally rewrites the conditions under which entire galactic families are born and evolve. Imagine a galaxy cluster. It is home to hundreds or thousands of galaxies bound together by gravity. Between them lies hot gas, radiating in X-rays. At the center of such a cluster, an active supermassive black hole launches jets that heat this gas and prevent it from cooling. Without this heating, the gas would condense rapidly, forming stars in overwhelming abundance. But thanks to the black hole, the process unfolds gradually, maintaining balance. This means a single black hole can regulate the destinies of... Philosophically, this gives us a startling perspective on the universe. We are used to thinking of black holes as ends, as places where everything vanishes. But in reality, they become sources of order, distributing the cosmos's resources. They are like gardeners, pruning excess growth and tending the cosmic landscape so it does not descend into chaos. The stories of observation here are especially impressive. In the Perseus cluster, for example, astronomers discovered vast cavities in the hot gas, voids hundreds of thousands of light years across. These cavities were blown by the jets of the central black hole. Moreover, sound waves were detected in these structures, the true voice of the black hole, vibrations propagating through intergalactic gas. They endure for millions of years, becoming a kind of cosmic music. Modern simulations reveal that without supermassive black holes, the universe's structure would look very different. Galaxies would grow too quickly, clusters would become chaotic, and the cosmic web would lack the harmony we see today. Black holes bring an element of organization into this grand design. Think of it, when we gaze at the night sky, we see mere points of light. But behind each point is a vast city, a galaxy, and at its heart sits an architect, shaping the fate not only of the city itself, but of the entire cosmic web. We are part of this architecture, particles in a design spanning billions of light years. In the next chapter, we will turn to the question of time. For the lives of supermassive black holes span billions of years, and their evolution is tightly interwoven with the history of the universe itself. In the previous chapter, we examined how supermassive black holes shape the cosmic landscape and influence the structure of the universe. Now let us turn to another crucial dimension: time. The lives of these colossi span billions of years, and their evolution is intertwined with the history of the cosmos itself. Supermassive black holes are not born in their final form. They undergo long journeys of growth and change. In the early universe, when galaxies were small and rich in gas, black holes fed voraciously. They grew rapidly, creating quasars, the brightest beacons in the cosmos. These quasars we observe today at distances of billions of light years, and thus we see them as they were billions of years ago. Over time, the reservoirs of gas dwindled, galaxies stabilized, and black hole activity subsided. Periods of quiet replaced the blazing quasar phases, but this did not mean the black holes vanished. They remained at galactic centers, ready to awaken at any opportunity. A merger with another galaxy, a massive cloud of gas falling into their gravitational sphere. Philosophically, it is reminiscent of breathing. The universe inhales and exhales through its giants. Periods of activity alternate with periods of quiescence, but the cycle endures. In this rhythm lies harmony, where even silence has meaning. The quiet of a black hole allows a galaxy to grow in peace, free from destructive outbursts. Scientists strive to trace this evolution by comparing black holes across different epochs. For this, they use the most powerful telescopes, including the James Webb Space Telescope. It allows us to peer at galaxies in their infancy and study the activity of their centers. These observations help answer the question: do all black holes grow in the same way, or does each follow a unique path? The stories of this research show how difficult the task is. To measure black hole activity in the distant past requires catching the faintest signals, photons that have traveled billions of years to reach us. It is like reading a book of which only fragments of pages remain. Yet even fragments reveal the breathing of the cosmos. Think of this, perhaps our own Sagittarius. A asterisk at the heart of the Milky Way was once an active quasar. Today it lies quiet, but in the future it may flare again. We live beside a giant that merely slumbers, yet has the power to awaken. Modern models predict that the life of a supermassive black hole does not end so long as its galaxy endures. Their fates are bound together. And this reinforces the idea that black holes are not only witnesses to cosmic history, but participants, shaping its course. In the next chapter, we will consider what significance supermassive black holes may hold for the emergence of life itself. For their energy, their balance, and their breathing may have influenced even the appearance of a planet where someone could one day ponder the fate of stars. In the previous chapter, we reflected on time and how the evolution of supermassive black holes is linked to the history of the universe. Now let us raise an even deeper question. What relation might these objects have to the emergence of life? At first glance, black holes and life seem utterly incompatible. Yet on closer inspection, it becomes clear. They may have played a crucial role in the appearance of life on our planet, and perhaps elsewhere. To begin with, recall that black holes regulate the growth of galaxies. Their energy prevents stars from forming too quickly. Without this feedback, galactic gas would have been depleted rapidly, leaving no opportunity for multiple generations of stars to arise. But thanks to black hole regulation, stars form gradually, giving the universe time to forge heavy elements, carbon, oxygen, iron. These elements are indispensable for planets and for life itself. Moreover, the powerful jets of black holes can stir the interstellar medium, distributing chemical elements throughout the galaxy. It is like a giant cosmic spoon mixing a vast soup of matter. Without this mixing, heavy elements would remain confined, and life might never have gained the resources it needed. Philosophically, this perspective is astonishing. Even destruction becomes a condition for creation. Black holes, often seen as symbols of endings, are in truth participants in the crafting of beginnings. They remind us that light and darkness in the cosmos are entwined, and one cannot exist without the other. The stories of scientists reinforce this vision. Research indicates that in galaxies with active nuclei, the formation of planetary systems may be particularly vigorous. The energy of black holes fosters the condensation of gas and dust into new stars, and around those stars, disks form where planets are born. Thus, central black holes are tied to planetary construction on cosmic scales. Think of this. Had our galaxy lacked its supermassive black hole, Earth might never have existed. The planet required generations of stars to synthesize heavy elements and mechanisms to spread those elements across space. In this sense, our very existence is linked to the invisible giant at the Milky Way's core. Modern models also suggest that black holes may help create regions where life has better chances of survival. Their radiation, for instance, can clear away excess gas, producing environments favorable for stable planetary orbits. Of course, excessive activity can be destructive, but in moderation, it becomes beneficial. The philosophical question is this: can life arise thanks to destruction? The cosmos answers yes. Life and death, light and darkness, creation and annihilation. These are not opposites but facets of one process, and supermassive black holes are among its principal actors. In the next chapter, we will turn to the paradoxes that black holes present to science. For the more we learn of them, the more mysteries they leave behind. In the previous chapter, we considered how supermassive black holes may have influenced the emergence of life in the universe. But there is another dimension to their story: the paradoxes they pose to science.
The more we study them, the more questions arise. And herein lies their greatest secret. They not only expand the boundaries of knowledge, but also reveal the limits of our understanding.
One of the central paradoxes concerns information. What happens to matter and light that fall into a black hole? According to classical physics, all is irretrievably lost beyond the event horizon. Yet the laws of quantum mechanics insist information cannot be destroyed. This conflict is known as the black hole information paradox. It has troubled physicists for decades and remains unsolved. Stephen Hawking proposed that black holes might evaporate, emitting what is now called Hawking radiation. But if a black hole vanishes, what happens to the information about what fell into it? Does it remain encoded in the radiation? Is it imprinted on the horizon of events? Or does the universe preserve it in some other way we do not yet comprehend? These questions are not only scientific but philosophical. They touch on the very fabric of reality, on whether the universe is fundamentally predictable or H. Another paradox arises from the internal structure of black holes. General relativity predicts a singularity, a point of infinite density where the laws of physics break down. But can nature truly allow infinities? Or is there new physics hidden within, waiting to be discovered? Perhaps black holes are gateways to theories yet unborn. Philosophically, black holes teach us humility. We are accustomed to thinking that science can explain everything we observe. But here we encounter a boundary, a place where our familiar equations fail. It is a reminder that knowledge is always limited, and mystery always greater than our comprehension. The stories of scientific debates about black holes are filled with passion. Some argued that information is lost, others that it is preserved. The debates unfolded at conferences, in papers, in public lectures. And though no final answer has emerged, the process itself has propelled science forward. For it is questions that give rise to new ideas, new experiments, new theories. Think of this. Perhaps it will be the paradoxes of black holes that lead us to a quantum theory of gravity, the great unification physicists dream of. Then black holes will not be dead ends but doors into a new era of science. In the next chapter, we will speak of the cultural meaning of black holes, for they have become not only subjects of science but symbols in art, literature, and philosophy. In the previous chapter, we spoke of the paradoxes of black holes and how they challenge our understanding of the universe. But these objects have another dimension, a cultural one. They have long transcended the realm of science, becoming symbols that inspire artists, writers, musicians, and philosophers. Today we will explore how black holes have entered human imagination and what they mean for our culture. The image of a black hole is mesmerizing. It is a place where light disappears, where time and space cease to exist in their familiar sense. For writers and poets, the black hole became a metaphor for endings, for the unknown, for the depths of the human soul. In literature, it is likened to an abyss into which a person gazes and sees their own fear reflected. Yet alongside this, the black hole also symbolizes hope, for from its surroundings comes the light of quasars, brilliance that traverses billions of years. Philosophers see in black holes a challenge to our understanding of reality. They ask, does the world have boundaries? Can we step beyond the known? The black hole becomes an image of the limit, the point where human reason meets the unknown. Yet it is precisely this encounter that propels science forward. As one philosopher wrote, where we meet darkness, there begins the path to light. In art, black holes find expression in paintings and in cinema. Recall the film *Interstellar*, where the black hole Gargantua was rendered with scientific precision and beauty. The film became a cultural milestone, for millions of viewers saw for the first time how a black hole might appear. For many, it was a moment of contact with the cosmos, where science and art fused into a single vision. Music, too, has been touched by them. Composers have written symphonies and electronic pieces inspired by the abyss. Rock bands have sung of gravitational chasms, while jazz improvisations sought to capture the chaos and harmony of accretion disks. The black hole has become part of the sonic landscape of culture. The stories of scientists who studied these objects have themselves become cultural myths. The name of Stephen Hawking is known not only to physicists, but to millions worldwide. His books, lectures, and interviews made black holes a symbol of humanity's quest for knowledge. He turned abstract equations into stories that touched hearts. Think of it. Why are black holes so captivating for the human imagination? Perhaps because they embody the mystery we always seek. We cannot live without enigmas, without horizons beyond which lies the new. Black holes remind us that there is always a frontier to move toward, and beyond it a space waiting to be discovered. Philosophically, they teach us both humility and inspiration. Humility because we realize not everything in the world is accessible to us. Inspiration because even where darkness reigns, beauty and light can be found. In the next and final chapter, we will conclude our journey. We will look at supermassive black holes as symbols of science, culture, and the human spirit. And we will try to answer the central question: what do they mean for us and for our universe? We have reached the finale of our journey. Across these chapters, we have explored how supermassive black holes are born, how they grow, how they govern galaxies, and even the structure of the universe. We have spoken of what they mean for science, for philosophy, and for culture. And now it is time to conclude and to ask the central question: what do supermassive black holes mean for us? On one level, they are purely scientific objects. They are laboratories for testing our theories, keys to unlocking quantum gravity, windows into the very essence of space and time. They confront us with challenges yet unsolved, and that is precisely what makes them vital. For science lives on questions as much as on answers. On another level, black holes are symbols. Symbols of darkness and light, of destruction and creation, of endings and beginnings. They remind us that even in the most shadowed places of the universe may lie sources of order, harmony, and beauty. They teach us to see the union of opposites, to understand that chaos and order are two sides of one process. The stories of the scientists we recalled are stories of the human spirit. People spent years, decades even, gazing at the sky, gathering data, debating, erring, and rising again. Their persistence turned the invisible visible, the impossible possible, and that inspires us. For if we have glimpsed the shadow of a black hole, what other horizons might lie open before us? Philosophically, black holes become metaphors for our own lives. We too encounter boundaries beyond which nothing can yet be seen. We too ask questions for which answers are not yet found. But it is those very questions that drive us forward. Black holes teach us not to fear the unknown, but to embrace it as an invitation to discovery. Think of it. Perhaps one day humanity will travel to galactic centers, observing black holes up close, probing their mysteries directly. Perhaps we will craft theories uniting quantum mechanics and gravity, and then black holes will cease to be enigmas and become doors to new worlds. But even if that day never comes, already now they fulfill their greatest mission. They inspire us to seek and to understand. The inspiring conclusion is this: supermassive black holes are not merely distant objects in the cosmos. They are mirrors in which we see ourselves. In them are reflected our fears, our hopes, our quest for knowledge. They remind us that humanity is a species that gazes into darkness and finds their light. Thank you, my dear listeners, for accompanying me on this journey. May these stories of black holes inspire you to seek your own horizons, to fear not the unknown, and to remember, even in the deepest darkness, there is always room for light.